Problem 27 asks the following. A circuit employs a silicon solar cell to detect flashes of light lasting 0.25 seconds. The smallest current the circuit can detect reliably is 0.42 microamps. Assuming that all photons reaching the solar cell give their energy to a charge carrier, what is the minimum power of a flash of light of wavelength 550 nanometers that can be detected? Well, let's prepare this way. I'm going to sketch out a circuit, and the circuit looks like this. I'm drawing the solar cell as a battery, and it works like a battery, except the current is driven not by chemical action, but by light. Light energy comes in, hits the solar cell, causes a current to flow, and I've got a circuit here which is going to measure that, okay? Now here's the thing. Each photon that comes in gives rise to a charge carrier. So if I'm measuring a current, that's the coulombs per second, that's a measure of how many electrons are going through the circuit. And that is a measure of how many photons fell here. So we can go ahead and figure out the number of photons, and therefore we can figure out the power of the flash of light. Now it's clear a useful piece of information for us is going to be the energy of the photons, okay? And to calculate that, I'm going to use this form. I'm going to use the hc over lambda, and I'm going to use the Planck's constant in joules seconds, because I'm going to want, ultimately, a power in watts. And so I'm going to have to work in joules and not electron volts. Now, if we do that, the energy of the individual photons here for 550 nanometer light, hc over lambda, if we work that out, my individual photon energy is 3.6 times 10 to the minus 19th joules. Okay? That's the energy per photon. Now, let's go forward. Let's do a solution here. The smallest current the circuit can detect is 0.42 microamps. Okay? Well, 0.42 microamps is 0.42 times 10 to the minus 6th coulombs per second. But we're detecting pulses of light that last 0.25 seconds. So I'm going to multiply this by 0.25 seconds. And that is going to give me the charge that flows. So 0.42 times 10 to the minus 6 coulombs per second times 0.25 seconds, that tells me the total amount of current that flows is 1.05 times 10 to the minus 7th coulombs. Okay? That's how much charge flows in one of these pulses of light. Now, we can also figure out how many electrons this corresponds to. This is how many coulombs, but if I divide by the charge per electron, and each electron, of course, corresponds to 1.6 times 10 to the minus 19th coulombs, that's the number of coulombs per electron. So if I take this number, which is the charge that flows, and I divide by this number, which is the charge on the electron, this divided by this gives me 6.56. And I'm going to keep an extra significant figure, times 10 to the 11th electrons. Okay? Well, of course, we're told that each electron arises from one photon. So that tells me I've got 6.56 times 10 to the 11th photons. That's how many photons are in the flash of light. Well, each photon corresponds to an energy of 3.6 times 10 to the negative 19th joules. So I take this number and I multiply by 3.6 times 10 to the minus 19th joules. This many photons times number of joules per photon gives me the number of joules in the flash. And if I do that calculation, I get this. I get 2.37 times 10 to minus 7th joules. This is the energy in the flash, but I'm not asked for the energy, I'm asked for the power. The power is equal to the energy of the flash divided by the time of the flash. Well, the energy is 2.37 times 10 to minus 7th joules. The time of the flash is 0.25 seconds. And so the power of the flash, this divided by this, and if I work that out, I get 9.5 times 10 to the negative 7th watts, that's joules per second. And to put it in a more reasonable unit, I'll write it this way: 0.95 microwatts. Okay? And let's do a quick assessment. It's a small current in microamps. And so we're going to expect that we're going to get a small power. And so a power in microwatts seems very reasonable. Okay? So our net result makes sense in terms of how the problem is phrased.